Welcome to an exploration of one of the most mysterious states of matter, quantum spin liquids. Imagine a material where the quantum spins never settle down, constantly fluctuating even at temperatures near absolute zero. This is a quantum spin liquid. Before we dive into spin liquids, let's understand what spin actually means in quantum materials. Every electron carries an intrinsic property called spin, which you can think of as a tiny magnetic moment. Quantum mechanically, electron spins can point up or down or exist in superpositions of both states. The magnitude of electron spin is 1/2 times the reduced Planck constant, approximately 5.3 times 10 to the minus 35 joule seconds. In solid materials, electron spins on different atoms interact with each other through quantum mechanical exchange interactions. In ordinary magnets, spins arrange themselves in simple, ordered patterns. In a ferromagnet like iron, all spins align parallel to each other, creating a strong magnetic field. This is the state of your refrigerator magnets. In an antiferromagnet, neighboring spins point in opposite directions, alternating up and down in a regular pattern. So what drives these spins to organize themselves? The answer lies in quantum exchange interactions. The Heisenberg-Hamiltonian describes spin interactions. J is the exchange coupling constant between neighboring spins I and J. When the exchange constant J is positive, spins prefer to align parallel, creating ferromagnetism. When J is negative, spins prefer antiparallel alignment, leading to antiferromagnetism. But what happens when the geometry of the material makes it impossible for all spins to satisfy their preferred alignments? Consider 3 spins on a triangle with antiferromagnetic interactions. If 2 spins point opposite directions, the third spin cannot satisfy both neighbors simultaneously. This is geometric frustration. Geometric frustration prevents the system from settling into a simple ordered state, even at very low temperatures. Certain crystal geometries like triangular lattices and Kagome lattices with corner-sharing triangles are inherently frustrated. The Kagome lattice, named after a Japanese basket weaving pattern, is one of the most frustrated geometries in nature. When frustration meets quantum mechanics, something extraordinary can happen. A quantum spin liquid. A quantum spin liquid is a state where spins remain dynamically fluctuating and highly entangled, even as temperature approaches absolute zero. Unlike conventional magnets that freeze into ordered patterns, quantum spin liquids resist freezing through quantum fluctuations. In a quantum spin liquid, spins point in constantly changing directions, creating a dynamic quantum superposition state. Why do these systems resist freezing? The answer involves quantum entanglement and the Heisenberg uncertainty principle. The uncertainty relation for spin components states that if one component is well defined, the others must fluctuate. This quantum uncertainty prevents complete ordering. Quantum spin liquids are characterized by long-range quantum entanglement between spins. Entanglement means measuring one spin instantly affects the quantum state of distant spins, even though they're not classically ordered. Entanglement creates invisible quantum correlations that link spins across the material, forming a highly interconnected quantum state. A simple entangled state is the singlet, where 2 spins are in a superposition of opposite configurations with a minus sign. Quantum spin liquids extend this entanglement to involve thousands or millions of spins simultaneously in complex superpositions. One of the most exotic features of quantum spin liquids is topological order and particle fractionalization. Topological order is a type of quantum order that cannot be detected by local measurements, only by global topological properties. Remarkably, the excitations in a quantum spin liquid can carry fractional quantum numbers, behaving like particles with half or third of an electron spin. A spin-on is a fractionalized excitation carrying spin 1/2, but no electric charge. It's like taking an electron and separating its spin from its charge. Conceptually, an electron can fractionalize into a spin-on carrying the spin and a chargon carrying the charge. These fractionalized excitations are emergent quasiparticles created by the collective behavior of many electrons, not fundamental particles of nature. Even more remarkably, quantum spin liquids can host emergent electromagnetic-like gauge fields. The spinons in certain quantum spin liquids interact through emergent gauge fields, similar to how charged particles interact via photons. The effective Hamiltonian includes emergent gauge field terms, where A is an emergent vector potential resembling electromagnetism. Emergent photons are collective excitations of the spin liquid that propagate like light, despite arising from magnetic interactions, not actual electromagnetism. This creates an effective theory of quantum electrodynamics emergent from the spin interactions, a stunning example of emergence in physics. For decades, quantum spin liquids were theoretical curiosities. Recent experiments have found strong evidence in real materials. Herbert Smithite, a copper mineral with Kagome lattice structure, showed early signatures of spin-liquid behavior around 2012. However, structural defects and impurities in Herbert Smithite made it difficult to confirm true spin-liquid physics definitively. In the last year, teams have reported much stronger evidence in pyrochlore-structured rare earth materials. The pyrochlore structure consists of corner-sharing tetrahedra, creating a three-dimensional frustrated lattice ideal for quantum spin liquids. Let's focus on cerium stannate, one of the most promising quantum spin liquid candidates. Cerium stannate has the chemical formula cerium-210-2-oxygen-7, where cerium provides magnetic moments. The cerium ions with their magnetic moments arrange on corner-sharing tetrahedra, creating strong geometric frustration. Multiple experimental signatures point to quantum spin liquid behavior in this material. First, no magnetic ordering is observed down to temperatures of 35 millikelvin, which is 0.035 degrees above absolute zero. This temperature is more than 100 times smaller than the Curie-Weiss temperature, which characterizes the spin interaction strength around 3.5 Kelvin. Second, neutron scattering experiments show a broad continuum of excitations, characteristic of fractionalized spinons rather than sharp magnon peaks. Third, the specific heat varies linearly with temperature at low T, suggesting gapless fermionic spinon excitations. This linear specific heat, C sub V proportional to gamma times T, is typical of fermionic excitations with gamma around 0.2 joules per mole Kelvin squared. Understanding why quantum spin liquids stabilize in these materials remains an active research question. Three key ingredients work together to stabilize quantum spin liquid phases. First, strong geometric frustration from the crystal structure prevents simple magnetic ordering. Second, quantum fluctuations are strongest for small spin values, particularly spin 1/2 systems. Spin 1/2 systems have maximum quantum uncertainty, making classical ordering most difficult to achieve. Third, competing exchange interactions at different length scales further destabilize ordered phases. Nearest neighbor J1, next nearest neighbor J2, and further exchanges create a complex energy landscape favoring the quantum disordered state. Let's quantify how quantum fluctuations suppress magnetic ordering. In a quantum spin liquid, the expectation value of any spin component is 0 due to quantum fluctuations. However, strong quantum correlations exist. Spins are highly entangled, not independent. Spin correlations decay as a power law with distance r, with exponent alpha typically between 2 and 3 for spin liquids. The correlation length exceeds many lattice spacings, often 10 to 100 angstroms, indicating long-range quantum entanglement. How strong are these quantum effects compared to thermal effects? We can estimate this using dimensionless ratios. When thermal energy kBT is much smaller than the exchange energy J, quantum mechanics dominates over thermal fluctuations. At 35 millikelvin with J around 3 Kelvin, the ratio is about 0.01, meaning quantum effects dominate by a factor of 100. How do scientists detect and study quantum spin liquid behavior experimentally? Neutron scattering is the gold standard, as neutrons interact with magnetic moments and reveal spin correlations in momentum and energy. The dynamic structure factor S of Q omega is the Fourier transform of spin correlations, revealing excitation spectra. Fractionalized spinons create a broad continuum of scattering intensity, unlike sharp magnon peaks in ordered magnets. Specific heat measurements probe the density of low-energy excitations, distinguishing gapped from gapless spin liquids. Muon spin resonance uses implanted muons as local magnetic probes, sensitive to spin dynamics on nanosecond timescales. Thermal conductivity can reveal mobile spin-ons carrying heat, particularly in materials with strong spin-orbit coupling. Cerium zirconate is another pyrochlore material showing promising spin-liquid signatures. Cerium zirconate, cerium-2, zirconium-2, oxygen-7 has similar structure to cerium stannate but different exchange parameters. The exchange constant in cerium zirconate is smaller, around 0.3 Kelvin compared to several Kelvin in stannate. It remains paramagnetic, showing no ordering, down to 20 millikelvin, which is 15 times below the exchange scale. These two cerium pyrochlores form a family of quantum spin liquid candidates with tunable parameters through chemical substitution. Theoretical understanding of quantum spin liquids relies heavily on sophisticated numerical methods. Exact diagonalization solves the quantum Hamiltonian exactly for clusters of up to about 40 spins, revealing exact eigenspectra. Density matrix renormalization group methods work well for one-dimensional and quasi-one-dimensional systems with thousands of spins. Quantum Monte Carlo uses statistical sampling to study larger systems, but suffers from the sign problem for frustrated magnets. Observables are computed as thermal averages using the partition function with inverse temperature beta. Tensor network methods provide a new approach, encoding quantum states as networks of tensors with controlled approximations. Not all frustrated magnets become spin liquids. What separates true candidates from imposters? First criterion: the material must remain disordered down to temperatures at least 100 times smaller than the exchange energy. Quantitatively, the freezing temperature should be less than 0.01 times J over Kb to rule out weak ordering. Second, excitation spectra should show broad continua characteristic of fractionalization, not sharp magnon peaks. Third, spin correlations should decay as power laws, not exponentially, indicating critical or algebraic spin liquid states. Fourth, the specific heat should show signatures of exotic excitations, either linear for gapless or exponential for gapped spin-ons. A major frontier is learning to control and manipulate quantum spin liquid states. Applied pressure changes bond lengths and angles, tuning the exchange constants and potentially driving phase transitions. External magnetic fields break time reversal symmetry and can induce transitions between different spin liquid phases or to ordered states. The total Hamiltonian includes both exchange interactions and Zeeman coupling to the external field with G factor around 2. Substituting different rare earth or transition metal ions systematically changes frustration, allowing exploration of the phase diagram. An exciting question is whether we can engineer artificial spin liquids in designer systems. Optical lattices with ultracold atoms or arrays of quantum dots could realize designer frustrated lattices with tunable parameters. Beyond fundamental physics, quantum spin liquids may enable revolutionary technologies. The most exciting application is topological quantum computing, where quantum information is stored in non-local topological degrees of freedom. Certain spin liquids host anionic excitations with exotic braiding statistics, which could implement fault-tolerant quantum gates. Braiding two anyons around each other implements a quantum gate through a phase factor e to the I theta that depends on the braiding path. The key advantage is topological protection. Information stored non-locally is immune to local errors and decoherence. A topological qubit stores information in the global entanglement pattern of many spins, not in individual spin states. Despite progress, many fundamental questions about quantum spin liquids remain open. A major challenge is definitively distinguishing true quantum spin liquids from disordered or glassy magnetic states. How many distinct types of quantum spin liquids exist? Theory predicts dozens, but experiments have confirmed only a handful. What microscopic details determine which specific spin liquid phase stabilizes in a given material? This mapping is incomplete. Can quantum spin liquids exist at room temperature? Current candidates require millikelvin temperatures, limiting applications. Room temperature is 300 Kelvin, vastly larger than typical exchange energies around 1 Kelvin, making high-temperature spin liquids extremely challenging. Quantum spin liquids connect to broader themes in quantum many-body physics. Quantum spin liquids are mathematically related to fractional quantum Hall states, which also feature fractionalization and topological order. Some theories propose that quantum spin liquid physics in copper oxide planes underlies high-temperature superconductivity. Adding charge carriers to a quantum spin liquid might produce superconductivity through the pairing of fractionalized excitations. Quantum spin liquids exemplify emergence, complex collective phenomena arising from simple local spin interactions. From simple pairwise spin interactions emerges a rich quantum state with fractionalized particles and emergent gauge fields. Let's summarize what we've learned about quantum spin liquids and their future. Quantum spin liquids are exotic states of matter, where spins remain quantum disordered down to absolute zero. Key features include long-range entanglement, fractionalized excitations like spin-ons, and topological order. Recent experiments provide the strongest evidence yet in frustrated pyrochlore materials like cerium stannate and cerium zirconate. These states are stabilized by the combination of geometric frustration, strong quantum fluctuations, and competing exchange interactions. Future research aims to find quantum spin liquids at higher temperatures and to engineer them in artificial systems, opening paths to revolutionary technologies.